Hi, welcome to my basement workshop where we're going to talk today about the lab you're working on this week in science. So the lab you're working on this week right now is called the Materials and Components Lab. And the idea behind this lab is for you to start experimenting with how different components and materials work. And as you understand more about that, then you'll start to understand more about how structures all together, how they fit together. So I'm going to present my screen and I'm going to show you, just before we get started, a little bit of a review of where we've been going so far. So up until now, we had been learning a lot about basically the forces that affect structures. So when a structure experiences external forces, so wind, people walking on it, an earthquake, or just gravity of that structure pulling it down, what it needs to do is it needs to basically keep its shape for it to be good structure. Otherwise, if it changes its shape and it changes it in a way that you didn't plan it, then you have what you call structural failure, right? So that's like when a bridge falls down, then it's experiencing structural failure. It's not supposed to fall down. For a bridge to work well, it needs to keep being a bridge. So the way that structures withstand these forces inside of themselves is in these sort of different ways: compression, tension, and shear. So some parts of a structure end up getting squished together, some parts might end up being pulled apart, and some parts of a structure might try to move side to side. We call these compression, tension, and shear. And you last saw these in our Planet Earth unit because these are the same forces that affect the crust of our planet. Compression happens at converging plate boundaries, tension happens at diverging plate boundaries, and shear happens at transform plate boundaries where there's lots of earthquakes. So these are not uncommon words for you. What we're going to look at today is we're going to look at each of the 5 experiments in your components lab, and we're going to talk about each one. I'm going to demonstrate each of the different parts for you so that you can kind of follow along at home, or you can take observations based on what I'm showing you. We're going to start by looking at experiment 1, which is all about the strength of different shapes. So what I've done is I've created a square and a triangle, and I'll have you take a look at these here. So I made these with just pieces of wood that I drilled holes in the end, and I just put screws through the end. But you could also easily make a component out of pieces of cardboard, right? And you could, nail the corners together, or you could, use thumbtacks, or you could, find some way, glue, tape, whatever, some way to connect these at their corners. And what you should notice when you start to play with these structures is that a triangle, if you apply forces to this triangle within the plane of the triangle, so that the force arrows would be like just moving, through the shape from the top, from the side, from the bottom, you'll notice that this does not change shape. If I apply forces like against the shape, so perpendicular, then yeah, you'll notice that this thing might bend one way or the other. But so long as I'm applying forces this way, this thing doesn't move at all. It's a very strong shape. On the other hand, if I take a look at this square, same idea. If I apply force, in the plane, we can see how this shape withstands the force. And what you notice is right away, if I apply force, this thing flops over. So this actually ends up shearing. The top and the bottom move in different directions. The structure fails. So in this case, this square, its strength is based very much on the strength of the joints in the corner, right? Each of these screws is what we call a joint, and we'll call these parts the members of the square. And even if the members are strong, if the joints are able to move, then this structure is going to move. Now, you might want that to happen, right? There are some structures that have moving components, and they do that deliberately. But if you don't want this structure to move, then you really need to pay attention to what's happening at these joints. Sometimes what you could do is you could create what's called cross bracing. So that's where you add a triangle to the shape. And now if you try to move the top and bottom relative to each other, you can't, because this triangle holds this in place. Another way you might reinforce this shape is you might just take like a layer of cardboard or some planar surface and put it right across this thing, and then it'll be less likely to shear as well. But on its own, it's not very strong because the joints are able to move. Whereas here, even though these are still screws through the board and they could rotate on their own, when they're all together in a triangle, they can't. These parts stay in the orientation that you put them in, and that makes triangles very strong shapes. So something for you to experiment with. You can try applying forces in different places, from the top, from the side, from the corners, and then start to think about how these structures fail. So is it the members that fail? Is it the joints that fail? If you apply too much force, what is it that breaks first and why? That's experiment number one. You'll just take some observations and play around with different shapes and how they produce different strength. Experiment number two. So this experiment is having you explore beams. So beams are members in a structure that span across a distance between two gaps. So I have, for example, a beam here. We can treat this like a beam. It goes from one support to the other support, and it spans a distance. And what that means is I can apply a force out here in the middle somewhere, right? These weights that I'm putting on here, they want to fall straight down, but they're supported by the beam in the middle. Now, what you might notice, though, with this beam is if I put it this way, where it's laying flat, when I put weight on it, it actually deforms, right? Notice that this sags a little bit. This is just a thin strip of wood, but it's actually quite bendy in this direction. And that's not really what you want in a beam. You don't want a beam that bends all that much. You notice that if you use this, there's a plastic ruler, exact same situation. They're very bendy in this direction. So the other thing you could do is you could take this and you could flip it up on edge. Now, when it's on edge, it wants to flop over. It's not very sturdy that way. But if you can find a way to support both ends so that it can't flop over, then suddenly this is a much stronger beam if it's being if it's experiencing force directly down, right? Some like gravity or something like that. So if you pull down on the middle of this thing doesn't really move. It's quite sturdy. And you notice that if you play with a ruler as well, same thing. You can't really bend a ruler this way, but you can bend it this way very easily. And that has to do with what's happening inside of this beam. So when I'm applying a force in the middle of this beam, I'm applying a force downward, what's happening is that the bottom of the beam is under tension. It wants to pull apart. So for this to be able to curve, the bottom needs to get a little bit longer and the top needs to get a little bit shorter. So the bottom is under tension and the top is under compression. And when it's on its side like that, that's very difficult for that to happen. If I push down on this, for the top to squish together and the bottom to pull apart, this wood would have to tear or rip, right? There's no way that it's going to be able to do that without the wood actually breaking. On this orientation, same idea, the top surface needs to kind of get squished together at the top, and the bottom surface kind of gets, pulled apart at the bottom, but they're so much closer together that they can make those little changes and the whole beam will bend. So you notice that if I apply my force here, you just see what my fingers are doing. Notice my top fingers move together, my bottom fingers move apart. It's the opposite the other way. Whereas here, if I try to bend this beam, same thing. I'm trying to bend it up, trying to bend it down. If I try to bend it down, the bottom tries to pull apart, and the top tries to push together, but I really can't do much with that, even though that's a very thin piece of wood. So the orientation of a beam matters. And what you'll notice if you have a basement in your house where you can go down that doesn't have drywall in the ceiling, like this one here, you'll notice that this is how we build the structure inside of houses as well. So the floor is supported by a bunch of pieces of wood that are on edge. In this case, we actually call these joists, but they're essentially working like a beam, so they're carrying a load across a distance. In a lot of situations, you won't just see simple beams where they're flat like this. You'll see a whole variety of other kinds of beams. And so this is where you might take a combination of these and put them together. So if I was able to glue these together, I could form a T-bar. And in that case, I have a nice flat top surface that I could stand on, or could be used as a bridge surface, but I still have that vertical section that really adds strength to this material. And so now these two things work together, and I get an even stronger structure that also has a nice stable surface. If I have one of these on the bottom, then I get what's called an I-beam. So there's lots of different ways you can combine these materials, but you notice that all of these beams have a sort of vertical section, because that's what really makes them strong. I'm going to show you an example here. So this is just a level, right? So it's designed to tell whether things are level or whether they're plumb, right? Plumb means straight up and down, or whether something is flat or not. And so the idea is that this is supposed to stay the exact shape that it is. It's supposed to stay super flat so that you can compare it to other things and make sure those things are flat too. So this cannot deform, right? It's designed as a structure to not change shape at all, or it's not a very good tool. If it's a bendy tool, it's not a good tool. And what you'll notice is, to accomplish that, this is basically an I-beam. So it's got this middle section, that's this thin layer of metal in between here, that's a vertical section. And then it's got a top rail and a bottom rail, and these are all just one piece of metal together. And so as a result, this is an extremely sturdy beam, right? Like you could put this across a gap and stand on this and it's not going anywhere. I think it's actually rated for something like 500 or 600 pounds. Very, very strong structure using the ideas behind beams. You're going to start to see these everywhere. So now that you're thinking about beams and spans, you're going to really start noticing, anything you look at, you're going to be thinking about, how did they design that so that it's strong enough to be able to carry that load? If you look at this, you can see that there's also different ways to support beams. So the ones that we've been doing, I've been showing you just simply supported beams, where it just balances on two ends. But you could also have, a beam that sort of sticks off and kind of, overlaps out without support, and we call that a cantilever. Kind of like a diving board, or maybe like the awning of a roof or a deck of a building. Those are like cantilevers. And so for a cantilever to work, again, the beam needs to be really rigid and strong so that it can experience force out at one end and not bend. A diving board is actually kind of a terrible cantilever because it bends so easily. But that's its design, and that's what it's supposed to do. If you designed a deck off of an apartment building that bent as much as a diving board did, well, you probably wouldn't get to keep your job designing decks of apartment buildings. So it really depends on the purpose of what you're designing, and then you really need to think about, what is going to allow for something to be as strong as it needs to be. If you're building a house or a deck, you're going to see that a house or a deck is really just a combination of these components all put together. So you've got, a flat surface on the floor that's made of maybe plywood or something, but that's not really where the strength of the floor comes from. The strength comes from all of these parallel joists, and those joists are spanning over a gap. And then often those joists are then supported by some even bigger beams that also span a gap. And so that way you only need a few posts to hold up this entire structure. Looks like this deck is being held up by probably 9 posts that holds the whole thing up. Okay, so that is beams. Beams are everywhere, essential part of structures. The second thing that you're going to look at here, third thing that you're going to look at. Oh, I just realized that I got this wrong. This should say experiment 3, not experiment 4. But experiment 3, which is about trusses. Well, a truss is basically just a bunch of triangles that have been attached together. So there's a whole bunch of different kinds of trusses. They look like this. They're basically like a way of making something that's almost like a beam, right? It's designed to span over a gap, But it's designed so that it doesn't use a lot of material. So it uses very little material, and the material is just put where it's going to make that structure the strongest. So if you are going to make a truss for yourself, you could do it the same way you made these shapes. Again, you could use some little pieces of cardboard and you could start to tack them together. And once you've done that, you could put together a truss, something like this. And so a truss, like a beam, can span over a gap. And in this case, if I apply a force to the top or to the bottom, like if I try to pull down from this or hang something from the middle, this is a pretty sturdy shape. Again, it's just made out of pieces of cardboard, but it's pretty sturdy. It's not sturdy this way. It's not sturdy this way, but it is sturdy so long as the forces push through the plane of the material. So like any force going like this way or this way, it's going to be able to withstand those forces. Okay, so here we have a truss. And again, if we load it from the top or the bottom, it becomes a pretty sturdy material. Now, the reason that these trusses work this way is the exact same way that the beams work. They're all about complementary forces of tension and compression. So if I flip this over, you can see I've labeled the different parts here. And the bottom of a truss is always experiencing tension when we're pushing down on it. And the top of the truss is experiencing compression. And here's how we know this. So if I go and I try to kind of hang something from here, so if I pull down, I'm pulling downward on this, right, the truss doesn't move. But if I take this top component off, this top member here, the one that I've labeled with a C, that is experiencing compression. If I take that component off, and I'll just move it out of the way, now if I pull down on the middle of this, immediately this truss fails. You can see that these two top parts, they move together. So these two parts are pushing together, which means if we want to stop them from pushing together, we need something in here that is going to resist that squishing. And, well, squishing is compression. So what we need is a component that is good under compression. Similarly, on the bottom, when I apply a force to this and the bottom gets pulled down, these bottom pieces are under tension. And I notice that if I disconnect one of these right away and I keep this like this, when I pull down on this, we immediately notice that this structure fails by these parts pulling apart like this, right? I pull down and it goes boom. So if I put a material in between that can be pulled on and will not move, then suddenly now I have a member that's under tension and this stays rigid as a result. So this is sort of a combination of experiment 1, which is all about shapes, and experiment 2, which is about beams that go across a span, because these work in very similar ways. So that's a truss. In the real world, you see these in bridges, especially train bridges, like this. And so you notice that this is basically just two trusses side to side with a set of tracks that go in between them, and then the trusses are just joined on the top. And so those trusses, with the force pulling down on them, they are not going to deform. That bottom part of the bridge is too strong to pull apart, and the top part of the bridge is too strong to push together. If you look at experiment number 4, this is all about arches and shells and domes. So for this, to make an arch, what you need really is just a piece of material that's kind of rigid, that is flexible as well. So you could use like a piece of cardboard and you could let it bend. I have a plastic ruler here, and you notice this makes a very good arch. Or you could use like a very thin piece of wood. Here's a very thin piece of wood here. And so that will form an arch. The idea about an arch is when you form an arch, you form it by taking the two ends and pushing them together. And that causes the top to move up. So now when this thing is actually experiencing force on the top, it's trying to undo what you've done, right? It's trying to push this flat again. And as a result, the two ends are going to push out. So if I push down on this, it tries to push the two ends away from each other. And so as long as those two ends are well supported, then this arch is very strong. But notice there, if when I push on this, the supports are able to move away, then this just flattens out and it fails. So this works so long as this is like one nice piece that can transmit forces all the way along it to both ends, and as long as the two ends are well supported. If they're not well supported, then the arch fails. This same idea applies if we look at a shell structure. So this is a cardboard tube, which is an example of a shell structure. And with this, it's not very strong this way, right? It goes pretty squishy this way. But this way, it's super strong. If I try to push on this, if I try to put the whole thing under compression, it is very difficult to push this together. And we can experiment with what's happening inside of here, what forces are happening inside of here to allow that to happen. So I'm trying to compress the whole thing. It does not want to compress. Why? Well, if you get a second piece of material, exact same kind of material, but for this one, put a cut in it. So cut up one side. And what you'll notice now is if I take this and I apply forces to it in the exact same way, you can very easily start to see how this structure fails. Notice that by trying to compress this tube, the cardboard wants to pull itself apart. It wants to kind of get fatter. And to do that, it needs to have these pieces move away from each other. So you notice for them to move away from each other, they're experiencing tension. And so when there is no cut in this, by applying compression to this, the outside material is able to stay together. It wants to get pushed apart, but it refuses to. It's able to withstand that tension that's trying to pull it apart. And so it's able to support whatever you put on top of it, right? So this would be like a really good post or a really good column, right? To hold a lot of weight, maybe at the end of a bridge, right? So you could have a bridge that is a beam through the middle and then a really strong post on either end, for example. But as soon as that shell is compromised, as soon as we cut the outside of it, then suddenly now that compressive force, well, now it's able to separate the outer shell and the structure fails. So there is an application of shell structures and arches, which work in sort of similar ways. They're sort of sending forces through themselves out to the outside. So the very last experiment that you'll do is one about corrugation. So you see corrugation when you look at a piece of cardboard. So if I were to take one of these components here, and you were to look through this cardboard, you would see the corrugations. Cardboard is just made of paper. Paper is pretty weak, right? If I just look at the top here, it's just one layer of paper with a bottom layer of paper and then sort of a zigzag layer of paper. Now, if I just take one layer of that paper off, like here's just a top layer of a piece of cardboard, this is like, has no structural strength at all. Whereas 3 pieces of that paper put together form up something that's pretty strong for how light it is. And the reason is all about that layer of corrugation in between. So corrugation kind of works the same way that a beam works, right? So remember, a beam works better if it's this way than if it's this way. Now, it follows then that a beam works kind of good if it's at a diagonal, right? If it's being loaded that way. And so if you took a bunch of beams and you sort of laid them like this, then, again, it's similar to having a bunch of beams laying all parallel to each other as they sort of all distribute the load together. So those corrugations work in a similar way as those beams by having that sort of vertical section. It's not totally vertical, but it's vertical enough in a zigzag that allows it to be quite strong. So what you can do is take a piece of paper and fold it like an accordion fold, like this. Now this is terribly weak this way. See, it bends this way. This would make a terrible bridge. But if I turn it the other way, and I made a bridge like this, right, so that my corrugations go along the length of the bridge, then this actually becomes pretty strong. Like I can't actually fold this too easily now. We'll just try something. If I put this here like that, right? So this could be like a roof of a shed or something. And as I apply a force on top here, the corrugations help to distribute that load. Whereas if I were to just take a single flat piece of paper without those corrugations, that structure is like very weak now as a result. So the corrugations are our way of using, again, similar principles to what makes beams and trusses work. But they're a way to create sort of a flat layer of material that's, still pretty sturdy, even though it has to span a fairly big gap. So try building a piece of corrugation like this. Try balancing it on two books like a bridge, and see what amount of force it can hold. And then pay attention to when it fails, how it fails. Does it fail in a similar way to how a beam like this fails, where it kind of gets flattened and then bends? See if that happens to be the case. So those are 5 experiments. And as you do those 5 experiments, you're going to take some observations. And the goal is that this will simply make you better at noticing the components and materials that make up all structures. So once you understand beams and you understand trusses and you understand shapes and you understand corrugations and arches and shells, if you understand posts as well, you pretty much understand almost every structure that exists. Every building, every bridge, every car, airplane, every bit of hockey equipment that's supposed to keep its shape under impact. Literally everything you can think of uses just some of those basic principles. So as you learn more about materials and components, you can really start to understand better all of the structures in the world and why they work the way that they do. So on that note, I wish you luck with this experiment. Take some time, play around, be creative. You don't have to have all the right materials. Just see what you can come up with. Like I said, a simple ruler or something like this is enough to be able to experiment with the idea of beams and what makes them strong in different directions. So be creative, see what you come up with, play around a bit, and see if you can build a more intuitive sense of how structures work. All right, and on that note, I'll let you go. Happy sciencing.